Kia ora, I'm Craig and I'll be doing a short presentation on the research project which I've been working on in the last 8 months. So here's a little background information. So currently there is little guidance in relation to the Rotorua soft soils and Holocene soil sites, which of course are problematic in geotechnical engineering. The latest study for the soft soils was conducted in 2010 and the scope of this did not include design approaches. So I've listed the main aims and objectives. So aims to express key geotechnical engineering methodologies and processes, and objectives is to express limitations in current New Zealand codes and standards specific to Rotorua's problematic soils. Ultimately, it is aimed to develop recommendations for geotechnical investigations and processes. So the two groups of problematic soils have been included in more detail. So Holocene sediments comprise loose sands and silts and are prone to liquefaction. They also have lower shear strength parameters and require specific engineering design. There's no good guidance specific to these soils in New Zealand, and many of these soils often lie on the border of mechanical properties. Pumiceous soils are difficult to determine liquefaction susceptibility, mainly due to the problems with CPT data correlations. This ultimately resolves around the fact that the soil particles in pumice soils are crushable. Although lighter in weight, pumice soils generally adopt a higher internal friction angle, which is in excess of 40 degrees for even loose sands of the soil. However, this is significantly affected by fines content. So liquefaction of saturated sands in alluvial deposits. Effects of liquefaction. They induce large sediments and lateral spreading, resulting in significant damage to buildings. About half of the Canterbury's economic losses were a result of foundation damage in relation to the Canterbury earthquake sequence. To mitigate these effects, where a natural crustal layer is not sufficient to provide surface manifestation, ground improvement can be used, and otherwise deep foundations can be designed. There's ultimately a snapshot of what liquefaction can do to a building in severe case. So results, I have downloaded, I've gathered some information regarding the soil properties at a site just outside of the Rotorua CBD. So the site comprised both Holocene and sediments and pumice soils. So here's the results of the liquefaction analysis. So this ultimately does not include the upper, there was about 5 meters of pumice soil because CPT correlations would not be efficient. So ultimately there was a high probability across 3 data locations on the site of liquefaction, and up to 310 millimeters of free field sediment following design level earthquake shaking was estimated based on software analysis. I have also created an Excel spreadsheet to automate pile capacity and settlements versus depth. This is on a basis of 0.5 meter increments. This includes effects of liquefaction, such as you can see how there is zero allowable capacity between about 3 meters of depth. That is due to the deep foundations cannot bear into these layers. These are based off B1 VM4 foundation design standard. So ultimately, my recommendations are to come out with a coherent guidance regarding these soils. For saturated pumiceous soil sites where it is economical to do so, I recommend to undertake cyclic triaxial testing to determine the liquefaction susceptibility. Also, seismic cone penetrometer tests in replacement of conventional CPTs may be used where pumiceous soils are expected, and applicability of shallow foundations, whether on a natural raft or an artificial one, which is a layer above the liquefied soil where there is sufficient bearing, to be determined using surface manifestation method. Thank you for listening to my short presentation.